Mm.
Okay, please start, Xianglin.
Yeah, so the paper I'm going to present today is called Neural Network Attributions, a causal perspective. So this is a paper from ICML in 2019. And the author is um, the sorry. So he's a PhD student from Johns Hopkins University, and his research interest mainly focus on machine learning interpretability and
So
explainability.
this work is only published by two PhD students.
No,
Mm.
I just erased the rest of
Oh,
authors. Yeah,
why
so
you
I
read?
just I just put two the first author and the second author here.
So is there's a lot of authors in this paper?
Um
I guess not, right?
Let me see. Sorry. So like
Um,
one, two, three, four.
okay, I suggest that we can put an order of knowledge, and I think all the authors was the credit, and of course maybe the first two authors are
Mm.
the main contributors, but the last two authors might be some big names. It's good as for us.
Okay.
It's good as
Okay, I
to
know.
know what kind of, and also you can in the AI community there's a lot of Indian people, and
Mm.
of course their name is not so easy to remember. So
Yeah, okay.
the more we get familiarized with those names, the more we understand the more we make sense of the community. Mm,
Okay.
mm.
So but here basically he's a PhD from Johns Hopkins University, and his research interests mainly focus on um the interpretability in mathematical methods. And also other students, I think they are from India Institution of Technology. And also the first
Mm.
author actually graduated from um,
Yeah,
this
yeah.
university
Mm.
in, to
I
complete his
understand.
bachelor.
There's always a way to
Connect.
build corporations by contributing the PhD students to some high-end universities. So this is a Hyderabad campus for an IT. You know, IT have a lot of campus across the India.
Is it a famous university?
IT is supposed to be the best, right?
Oh,
So,
okay.
Xianglin, is that IT is supposed to be the best university, just like the Tsinghua University in India, right?
Something like
Something.
it.
Mm,
Oh,
mm,
okay. And yeah, so today basically because I found his slides, I think it's a very good detailed slides, so I just adopt his slides
yeah,
too.
yeah, that's
Yeah.
fine. As long as you can really explain it.
Mm. So basically the contents contains eight parts from introduction to conclusion. So I'm gonna just start from the introduction. So deep learning methods highly successful in solving very complex problem, but the interpretability um, really prevents widespread adoption. So here today, this work concentrates on the attribution problem, which means um, in if you have a deep neural network and you choose an input neuron and you can also choose an output neuron and you wanted to know the causal attribution caused by the input neuron you choose to the output neuron. So that's called um, attribution method. And they claim that this is the first effort on a causal approach to attribution in neural network.
Last year,
Hmm?
so last
Last
year,
year, yeah, last year.
first effort on the causal approach. Wow, it seems a big claim.
Yeah. Yeah, because they said some other attribution methods are more more like to explain the relationship between the input neuron and output neuron, but um ex- they they can give you a
Okay.
causal.
Mm.
Yeah, so that's
They
the difference.
so that means causality trumps the association, right?
Mm.
Mm. You still prepare two questions for the audience here, right?
Uh,
Hmm.
I kind of
Maybe you can.
maybe I can raise some questions when.
Yeah, maybe you can think of the questions on the fly. Yeah.
So and then the prior work there, depending on what kind of technique are used. So existing method can be divided broadly into two categories. One is called perturbation-based method, and the other one is called regression-based method. So the perturbation based method mainly means to perturb the input signal by a small amount, and then you observe the change in your output. And the regression-based method just means you use a different classifier that performs similar functionality with the model you try to explain, and then um, because the classifier you used might be, for example, decision trees, and therefore it could be interpreted by a human. So in this way, you kind of use a simpler classifier to explain the more complex model.
Hmm.
Yeah.
So maybe a question here is that
Mm.
is there anyone can think about another way to using an auxiliary interpretable classifiers apart from the deep learning, apart from decision tree? Is there any other interpretable classifiers here? Is anyone here can answer the question? So what kind of classifier? Definitely for the neural net model, it's very hard to be interpreted. But for the other traditional machine learning models, and what kind of model do you think it is more interpretable? Yeah, you have a recent example, decision tree. And is there any other
You're asking
interpretable?
me or Alex?
I think anyone can answer. Maybe
Yeah. I
maybe.
think, for example, like
Mm,
linear SVM
mm,
or just those traditional machine learning algorithms, SVM
mm.
or
Maybe you can ask someone.
NUS.
Maybe you can ask someone. So, for example, Ruofan,
Like Rofan.
Ruofan, will you please raise another example of the interpretable classifier?
Hmm. I- interpretable means
Uh,
Like simpler.
simpler.
Yeah.
K nearest neighbor.
nearest neighbors. So it's for
Hmm.
classification. Mm.
Hmm.
Okay, so you
Yeah.
think so you can we can classify based on its neighbors.
Hmm.
Somehow reasonable. Maybe 正风.
I
Can you raise another examples of what do you think? What do you think? What is a more another kind of interpretable classifier?
To my knowledge, I think the decision tree is one of the classifier
Mm.
which has the highest uh, interpretability. Yeah.
Mm.
So maybe I can raise another question here. Do you think
Mm.
random forest is an explainable classifier?
I think random forest is less explainable compared with decision tree,
Mm.
but somehow it still has it's more interpretable than the neural network. Yeah. So yeah,
Yeah.
so I think that's a
Mm.
decision also. Yeah.
Okay. Okay. So maybe please go on. I
Mm.
agree. Mm.
But here comes the question. So if you have a um if you have a attribution interpretable method and you have some result, but how can you know if, for example, if there's an error, how do you know this error comes from the data set or your neural network structure, or is it because your method has some problem, so you cannot know? So here they propose five new um, five new methods to um, to evaluate how good your attribution method is. So basically, it's conservativeness, sensitivity, implementation invariance, symmetric preservation, and input invariance. So that means The first one, conservativeness means, for example, the your input has some features, and if you change each features, and that would change the outcome, right? So um, all the change you made to your input should be reflected by the change in outcome, which means your the prediction result of your input minus the baseline of the output.
I mean, that means you give me a delta x, you need a significant delta y to make sure these x or this input or these dimensions can
So
attribute.
that just
Mm.
means your um per, the perturbation on the input should reflect on the output, and that should be conservativeness.
So why they call it conservativeness? So this
Um,
is seems a very straightforward perturbation-based approach, right?
yeah. So that's just a how to say it. That this is the attribution to measure how good your method is.
Mm.
Yeah.
Okay.
And the sensitivity means if you change some
Sorry. So maybe I'm doing further. The conservativeness or completeness, and maybe
that's the
maybe maybe
same.
yeah, maybe is that I who mistaken.
Mm,
So given an x, given an input and baseline means is another kind of input, right? So
yeah,
for comparison,
just you.
and the input is actually a perturbated version of the baseline. Or
Yeah, yeah,
am I correct?
yeah.
So, and what does I
Um,
means? Giving your equation, what does I mean?
I is different features in your input. For example, you
Mm.
have I
So, for example, I
mm,
have 10 dimensions.
features. Mm,
So I perturbate each dimension and to observe whether the outcome has been changed.
mm,
So I sum up all the dimensions together.
mm,
So somehow I can link this process with the name of conservativeness and completeness.
mm. How to say? That
It's
just
more.
means. Mm.
It seems to me more like a sensitivity. So when I
Oh,
perturbate
the
the
sensitivity here means if you change the input and then your output changes, right?
mm,
You can somehow calculate a gradient based on those change.
yes,
So
and
that
so
means that is
mm,
sensitivity.
and can you market and market our sensitivity and what's the difference between the sensitivity and the conservativeness?
Um, I think for the conservativeness, that means um, your the change in your output can only comes from the change can only comes from your change in the input. Not
So can you raise an
some else.
example? So what do you mean by can only change?
From my understanding, how to say it? The conservativeness just means 守恒, right? 就是
Mm.
like
So yeah, I understand
they cannot.
some properties actually be preserved, right?
嗯
Some property be preserved. So that means whatever. So that means whatever we change it an input, and we always need the output will be preserved. Will be preserved.
嗯
Is my understanding correct? Or if you're
I think that's
if
correct. Correct.
mm,
And those five um, new methods are
mm.
how to say. I think they are just used to evaluate how good their method is, but um,
Anyway,
it
so here
didn't
let's come
affect
back.
our
Let's
understanding on.
let's come back to the logic of these lines. So the question these slides raise, because you are not the author of these slides, so I believe, and the author of the slides is actually the author of the papers. So I guess the logic here is fine. All what we're doing is actually we're interpreting what is this slide, what are those points that the authors want to convey. And the question is here, how to distinguish the erroneous network and erroneous, and where there's an erroneous evaluation matrix,
um they
right?
they said if their method can follow the five, how to say,
Property, more like it's more.
properties. If their method can't follow the five properties, then they are sure that if um there's an error, then it is because of the neural network, not because of the error in their proposed method, in their.
So that means if we, so let me interpret your point here. So when we say, for example, when we say that there's an error in the network, so there are two possibilities. One, the network has an error indeed.
Yeah.
The second, your approach has some
Yeah.
mistakes. So once your approach report there's an error in network, there are several ways for us, several methodologies for us to use to decide whether our approach is correct, whether the output kernel approach is correct. And I think I feel that I need some examples. I do feel that these slides are a bit dry.
But actually, they didn't give any examples on those five properties. They just list all the properties in their paper, and when it comes to.
Yeah, but anyway, when you read the papers, it is your responsibility to go through to digest this point. So for now, I think we still have some confusions on what is conservativeness and completeness, and it's quite easy for us to digest what is sensitivity. And maybe we can leave this point. We can hand on. We can get over the conservativeness. Maybe you can start explaining the.
Actually, they said their method didn't follow the first property.
And whatever. So would you please go with the third point, implementation invariant.
Okay, so that just means. Oh, sorry. Just wait a second, sorry. Okay, so the third one is called implementation environments. So that means the attributions are always identical for two equivalent network. That means if we have two network, and for each the same input, the two network would output the same, so they performs the same in terms of functionality, and your attribution method should should be the same for the two network. Yeah.
But so that means the semantics of two networks are exactly the same.
That means they didn't care about the
internal
details, the internal details in the network. As long as the input and output are the same, then their attributions method will gives you the same result. Yeah.
Okay.
Yeah, and for the symmetric preservation, that means, for example, if the input of the neurons can be changed and the outcome would be the same. For example, if you have a function of x times y, then the x and y are interchangeable. And then the attribution method should gives you the same result for the two inputs.
I understand the xy for the equation x is times y, x y is exchangeable. So is there an example?
I would also give you, yeah, actually I have an example. For example, here the f would just be x1 times x2, and then just by compute the grade, for example, we have input a equals to 5 and 1,000, and by computing the gradients for x2 would be 5 and the gradient for x1 would be 1000. That means x1 so that means they have different influence on the outcome, but that's wrong. In fact, the x1 and x2 should have the same influence. Yeah.
So
So
these slides mentioned that gradients may not be reliable.
yeah, so
It's
that's
not,
how they said we shouldn't use gradient.
and
So
how this links to the symmetry invariance.
so I think from their method, the influence of x on f, x1 on f, or x2 on f should be the same. Because
Okay.
here they gives the one is 5 and the other one will be 1000, and they think that's wrong.
Okay.
Yeah.
Somehow still, okay, the symmetry preservation. So
Mm.
somehow, you mean, so here your point is that the gradients does not conform to the property
The
of symmetry.
gradient can only tells you somehow the relation
Mm.
that x1 has some influence on the f and x2 has some influence on the f, but they cannot tell you the how much it contributed to the f.
Okay.
And you cannot get that result from one single input. And we will talk about their method later. And the input variance, actually, I didn't check the input invariance because I don't think that would um, uh, that's very important.
Basically, I think despite your work on the visualizations, but our visualization is going to explain on something, right? And so the quality stuff is also very relevant. So all what we do is going to explain. So somehow when you do the visualizations, when we work on the visualizations, and you think about your thesis, definitely have a word of causality. Maybe in the visuals, maybe we can provide the word like visual causality for the neural network models, and all these properties will be very important. And I highly encourage you to go through every detail there. So maybe you can share the paper again in the groups, and then I think for
Yeah.
Ruofan
And it
Ruofan
just
and
because
Zhengfeng can still have a chip for that.
yeah, I know, and just because of the time limitation, they are all from this paper. So I did check on that paper, but I didn't check on this paper. So yeah. But
Maybe
anyway.
maybe on the Thursday meetings, maybe you can explain a bit
Yeah, I
more
can
on the property.
explain it in more details later. But anyway, I think that wouldn't affect our understanding on their methods today. Yeah. And this method integrated gradient is their baseline. So they said this method can follow the first 4 properties.
So have you understand what is integrated gradients?
No, I didn't check this paper.
I checked it once, but I forgot the concepts like frankly. And also for Ruofan, Zhengfeng, Wei Qingzhou, and actually all the students, I suggest that you investigate what is integrating gradients. And the idea of integrants is kind of brilliant, and it seems that it's the best paper, if I remember correctly, the integrated gradients.
In
So
that year.
yeah, the gradient itself is not so intuitive. It's not so sometimes will provide some misguiding signals, but integrated gradients can solve the problem in a somehow perfect way. Okay, please go on.
Okay, so they think that the current attribution method exhibit implicit bias. They think, yeah, given for example a neural network to map from d dimension to one dimension, and the how to say, just like this example, when you wanted to know how much x2 would influence f, it would be, the outcome would be also influenced by the value
Value
of
of
x1.
x1.
Yeah. So they think the first method, the perturbation based method would be influenced by other input features. And for the regression based method, they think the regression method can only capture some correlations rather than causation. Mm. So that's why they propose their method called average causal effect. So here they interpreted neural network as a structural causal model. Later we will explain what is structural causal model, but basically, how they answer the problem of causal effect is, um, you chose an input which is xi, and you randomly sample some value, and then you observe the expectation of the outcome y. And here, just means the baseline actually. So you sample some random values of one input neuron, and you calculate the expectation of the output y, and uh, and by minus the expectation of the baseline. In this way, you get the relative difference. Uh, yeah, so that's the idea they gave.
Xianglin, can I ask what is do here?
Do just means you change the xi.
As
So xi have some
Hmm.
values, and then you sample some random values for here, for example, alpha. So that just means you change the value of xi to alpha, and then you observe.
But here the alpha is fixed, right?
Alpha is what?
The alpha is fixed. So
That could means any values.
I understand
So the
alpha
do,
can
yeah.
be so the alpha is a random variables or a fixed, it's a random variable.
So they sampled xi from a uniform distribution.
And observe the expectation of y.
Yeah. Because remember that they
But
said,
here you can see xi is the random variable itself, right?
Hmm.
So here we would like to assign alpha, the value of alpha to xi. That means, so maybe I misunderstood it. So from my understanding, so that when we fix xi and we randomly sample, because maybe the network has a lot of the other values, and we change the other values, and so
we would talk about that later. So actually they use the mean the mean and covariance of the whole training data set and decide what's the other variable is.
Why beta is also a random variable?
Later we will talk about that. So here, this one would be the baseline. And yeah.
And can you raise some examples? For example, the alpha and the beta are actually the feature is actually the input, right? Alpha. So alpha is a random variable. Am I correct? Am I correct?
Yes.
And
but the beta, we will fix some value for the beta later.
So if alpha, so this beta is also a random variable.
Beta.
So for example, when I say random variable, that means we sample. That means alpha can be randomly sampled, and but giving alpha and beta, and they may conform to different distribution. For example, alpha conform to the random the uniform distribution.
I think this equation is somehow confusing, but actually what they did is sorry, they fix it. They find a baseline xi and they use a fixed value.
So the beta is fixed value.
Yeah.
And
they,
the
here we only have one random variable.
Okay.
Yeah. So let's talk about the structural causal models first. So the structural causal models have four factors. X means endogenous variable. That means it's hard to explain, but you can see that, for example, we have input x10, x11, x11, and x12, and that's exogenous variable. That means those variables comes from our observation, and they are undetermined. However, if we get the value of x10, x11, x12, and then we have some fixed function, and then the x1 to x6 is fixed, and we call those variable as endogenous variable. And we also have causal functions and the distribution of u, which means the distributions of our input. So all those factors forms one structural causal model. Is that clear? So do you have any question about this? So they just view a neural network as one structural causal model.
Please go on.
Yeah. So so here, for example, if we wanted to know the x2, how would x2 infect, for example, x8, and then we can randomly sample the value of x2, which you can see that its connection to its parent nodes are disappeared. Yeah. So here we just randomly sampled x2 and observe, for example, the x8. That's how the do functioned. Yeah. So this page just tells you how that do operator functions in our equations.
Wait, so there's some questions I'm explain. So px1 to pxn, and what does that mean?
Oh, here it just means the value of x1 to x6 is determined by the input, just the input, just the given input. But if we assign some values to the xi, here for example the x2, then the probability of, or the value of x2 would be dismissed from this equation. So the other one, the x1, x3, x4, x5, x6 performs the same with the original network. However, we just remove the x2.
What is the delta here? Delta xi minus xi.
So I think that's a fixed value. So
so what is the big P and small p means? So the balanced network model theory, the G and P. So is that a typo? So
is that what?
The typo, I mean the first bullet. There's a big P and small p here.
The piece, the small piece, I think it's the distribution of some endogenous variable, and so this distribution comes from the function along with our input, so you can calculate like here I can give you an example. So if we observe x7, then its probability would be can I annotate?
I thought I cannot annotate on this.
Yeah. For example, if we observe the x7, then the probability of x7 would be p would be a function of x1 to x6, right? And x1 should be x1, sorry, and then we can calculate px2 and px3. And then the probability of x7 would be px1 times px2 times px3. So that's my understanding. If I'm wrong, maybe Rofan, you can correct me.
So this n is 6, right?
Which
small n, x1 up to xn is essentially x1
yeah, I
up to
think
x6.
that, yes.
Yeah, and they are independent, so the joint distribution is equal to the multiplication. And all of them are dependent on the exogenous variable x10 to x12.
Yeah.
Yeah.
Yes.
And still have and how about the delta big xi minus xi? What does this delta mean? The delta is still probability, right? Or is it just more like a discount?
So because we sampled some values for the x2, so the probability of x. So I think this value depends on how we sample x2. Yeah.
Well, I think it's fairly clear now. And the other one has a question here. If no, let's keep going on.
Let me erase my annotation. Yeah, so and here it means we can, if so here, for example, if our original neural network looks like the left one, and we wanted to observe this layer as input and this layer as output, and then we can write it, we can simplify it to the pictures on the right. And how to simplify it? It just we can just how to say this? We can write the function. So here I gives you an example. We try to observe J, then J would be the G would be this function, and H would be this, and I would be this. And here we can write J as a function of GHI, which you can just feed those functions here. And then we can write J as a function of a to f. So this f could be a new function, but in this way we can simplify it as the right picture.
So what a G means?
Huh? G
What G? I
G
heard.
H I just some
Oh, okay, G is
hidden layers. So
okay.
if we can know each functions, we can always simplify it as the
Okay.
right form. So in this way we can yeah, it just simply. So if we can view every neural network as the form of the right picture, and then we can yeah, like discuss later. And also for the recurrent neural network, they can simplify it as the form like this. So I think not much to say here, right? You can write it as a form like structural causal model.
We can skip the recurrent network here, but anyway, it's going to be just a split the
Yeah,
neurons.
you just write it as the form of structural causal models. And then we can define, remember our goal is to find the causal effect of one chosen input to one chosen output neuron. So here y is our output and xi would be our
So
chosen
here the
input.
return value, the mark return. So given input, so here for our problem, so I'm talking about the problem definition. So for the problem definition, we give an input neuron and output neurons. We're going to say whether there's a causality relation between input and output. Right. So here I'm talking about the problem definition. The problem definition is that given an input neurons and an output neurons, whether the change of input will cause the change in output. Is that how you define the causality?
Yeah. So just like this picture, if we chose like for example B and we observe J here, then J, the value of J would be Y and B would be XI.
So actually it's just report true or false, right?
Not true or false, they calculate the value. The value is called average causal effect.
So there's no exact yes or no questions. So it's
they
how
just,
much
the value is
how much causal effect will this
so
input on
that's
this?
yeah, so
Okay.
that's the value of average causal effect. So that just calculates this. So this is their method. So each time if here if we get the baseline xi, suppose we have the baseline xi, we would talk about how to calculate this baseline. But suppose we already have a baseline xi, and we randomly sampled the xi, and we observe the expectation of the output y, and then by minus the baseline xi, we get the average average causal effect.
So that's how they define the average causal effect.
Yeah.
And
so I
that's
think
all?
I think this equation is the core of their method. And later we will talk about how to calculate this equation. But basically, yeah, I think so the idea is quite straightforward, I think.
Wait, let's go back to the average. No, just do the slides. And for this binary, that is for the xi to be either 1 or 0. And
So
for when how is this do xi equals 1 means? So that means xi can only be sampled as 1s, and we observe all the value of y.
yeah.
So when we if, anyway, so if xi is equals to 1, that means xi cannot be any other values, because
Yes, yes,
it,
yes.
it will not be 0 anymore.
Mm.
So given that y is the random variable, so that means that means we will not change x, but that means we can change all the rest of the xj, and j is not equal to y, and we're going to observe
The
its
expectations. Yes.
and then we fix xi equal to 0, and then observe the expectation of y,
Mm.
and to see their difference. And
Mm.
if there's no much difference, there's no causal event. Otherwise, okay, so it's more like a statistic evaluation.
Mm.
So it largely depends on how we sample the rest of xj.
Oh, sorry, can you repeat?
So the causal effect is more depend more depends on how we sample the rest inputs.
Mm.
For
You mean
example,
other? You mean
and
you mean
neuron, and then,
XJ? You mean
yeah,
XJ, right?
yeah, xj, because there are a lot of xj, and
Yes.
it depends how we sample those xj.
Mm.
And I suppose there is a very large range. Of course, if it is a random, if it is still binary variables, 0, 0, 1, 1, 0,
Mm.
and there are still
So the
a large number.
most intuitive way is just to go through your entire training data set. That means you fix the xi for here, for example, for 1, and you calculate the whole, for your whole training data set, you calculate the y and you get the mean of y. That's your expectation of y. That's the most intuitive way, but that would be very computational expensive. So what I do later is here they explain if you just use one input vector, that is called individual causal effect, but they wanted to calculate the average causal effect. So that just means they will go through the whole training data set.
Okay, let's go back to the slides one by one.
Mm.
Previous slide. Okay, so we'll please start with explaining the adaptive baseline. So there have multiple baselines here, right? That means
So here
mhm.
if you have some domain related knowledge, you can assign the xi with some other method. But here, how do they choose the xi is because the xi is sampled from a uniform distribution with a predefined value low I and high I, and um, here they just use the xi head is just I think it's the average value of yours sampled xi, and you calculate the expectation of y, and that's your baseline xi.
Okay, I see.
Yes.
Mm. Okay.
This page just explain if you use some if you just use one input vector, that is called individual causal effect, and that would cause the gradient problem we talked about before. So they think this is a
Why?
bad
Why?
idea.
So that's, you mean the y is individual?
No, here if you change the xi to alpha, for example, and for the rest of features xj, you use just one input. You use the value of one input vector, and the value would be the outcome is called individual causal effect. So here, for example, you have um, the u. For example, if you have a feature x1, x2, to x10. For example, you have 10 features and you choose, for example, fx2 and you assign it to alpha. And then um, you calculate the y and also the y if you don't change x2. So here you just, the u is just the original input and you calculate the difference between them. And that's called individual causal effect because you only use one input. But however, in their method, average causal effect, they 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 change the value of xi to alpha, and then they go through the whole training data set and get the average value of this causal effect. So that's the difference.
Anything about it. So what
Mm.
we talk about is that for the previous ACEs, for x2 is equals to an alpha. So we compare the expectation when x is equal to alpha.
Here is not an expectation. U is just one input vector, and you change the you change one features to alpha,
Mm,
and of course you will get a value of your output neuron,
mm,
and
okay.
yu is yu
It's a normal input.
yes is the normal case, and you calculate their difference. But in average causal effect, you do not do it just once. You do it for your whole training data set, and then you get the mean of the difference.
Okay, so that means, okay, so it's used another way to illustrate what is gradient-based approach.
So like in our previous example, we have xi times x2, and xi is equal to 5 and x2 is equal to 1,000. And if you just use one input, that would cause some problem. So what they do is they use the whole training data set and hope that would mm,
So they, so
they,
the factor 1,000 will be offset, will be offset, right?
yeah.
So we, so for example, the baseline is x equals to 100,
And
and
x2 is also equals to 100, right? For example.
but x2 could be a random variable.
Oh, you mean okay.
X2 is actually a random variable. So in this case, if we fix x equals, suppose the baseline is 100 and suppose the baseline of x1 is 100, and we can fix x equals to 5, right? So then we compare, then we go through the whole training set. And in this process, the x2 can be either 1,000 or be 100, etc. So we compare based on, when we compare these two cases, how the expectations of the output will be changed, right? If the expectation of these two cases are still remain the same, that means getting the change of x1 is actually doesn't matter to the output. So the causal effect will be very small. Otherwise, the causal space will be very large. So it's more like an average gradient, right?
Yeah.
So
So
consider all the cases.
yes,
But
yes,
but
yes.
yeah, but this idea is also a little bit similar to the integrated gradients. But maybe you can, maybe I
Yeah,
will
I can
investigate.
check on that paper later. Yeah.
Yeah. So the idea is more like this. So the idea is that it's using a weighted sum of the gradients. So maybe it changes the value a little bit, observe the gradient, and change the value a little more, then observe the gradient. Then it is sum up, it's more like integral. It's more like calculus. Then it integrate all the gradients and take the integral gradient as the final gradient instead of using the gradient itself. Maybe the similar idea, that means it's still sample more, but introduce more introduce more on computation cost to have a more general results. Okay, please go on.
So then to go through the whole training data set would be very computationally expensive, and that's how they propose. Um, Here you can see that the expectation of y is just the mean of every y we calculate, and it will be very costly. So that's why
Sorry,
they.
can I digest the formula here? The
So
formula
so
is
so actually, you to calculate the expectation of y, um, by definition, it looks like this, right? For every mm,
yeah, that's expectation.
yeah, it just the definition.
There's a
So it's very
definition.
costly. So it just the whole slice just means you go through the whole training data set and you calculate the y, but it will be very costly. So by doing a second order Taylor series expansion about mu here, xi about no, sorry, li is one single input, but mu is the mean. So for example, if we have 10 features, the mu would be mu1 is the mean of feature 1 for your whole training data set.
Mu is a vector. Mu
Oh,
is a vector.
yeah.
Mu is a
So
vector.
mu is one input.
Okay.
Yeah.
So it's
So
there
each value is the mean of that features in your whole training data set. So they calculate this value in advance. Mm.
keep going on.
Yeah.
I'm still waiting for explanation.
So yeah. So by doing the Taylor series expansion, the uh output y for input li would be look like this. So right. Do you have some questions?
Of course, I have questions, but I'm thinking about how to ask it.
Mm.
So here's the y, the fy, the derivative of fy. That means how do we interpret the let y equals an f derivative x1 to xk? So why we need such a derivative here?
What? Where?
The second line.
The second line.
The second line of the whole slice.
This line.
Yeah.
So what's the problems here?
So what's the point here?
So because to go through the whole training data set is very costly. Here
So
we
what's the
try
goal
to
here?
find.
So we would like to calculate the expectation, right? So you're talking about how to optimize the calculation.
Yeah.
Right. So here, so why we need such a derivative? So how is derivative is used here? So given an xy to xk, and so for what is the variable of this? Sorry, can I stop the sharing and will you please restart it? Because I cannot mark it. Will you please restart it?
Okay.
Restart your sharing.
Mm.
Why cannot mark it?
Let me stop it.
Maybe you can share it. Maybe you prevent my marking.
Can you see my slides?
No, I cannot. I can see slides, but I cannot mark it.
Why? I didn't do anything.
But keep going on. Keep going on. Maybe I can ask here, and you can keep marking. Here the point is that so y is an output, right?
Why is not?
Y is an output.
Yes.
Y is output, and what is fy? So when we calculate the derivative, what is the derivative variables on what is derivative? What is derivable durable?
Uh, you mean, mm,
Yeah, so we can see this is derivative, right? F prime.
this one or this one?
I think so F is
Um,
not there. Sorry, the F is not a derivative. So
no,
why
no, no.
why is that a
Fy
F prime?
prime
So
is just a function on how to calculate. I can just write it like, if here this is our output, and we have many x1, x2, and for example, if we try to sample this one, and we have xn, and they all contributed to y, and then we can write it like this, right? So y is just here is just the function of the neural network, and to the process of calculating the y is very costly. So here their goal is to try to optimize this process, and
the process of calculating
the
y
y.
is going through all the train sets, go through all the train sets. Because
So
calculate one sample is not very complicated. We just perform the forward propagation to get the value of y.
but in the end, they tries to, for example, if in the experiment section we would wanted to see a chart like this is the alpha and this is the uh, average causal effect, and then what they did is here they choose some alpha, for example, they choose some alpha and get the I don't know, for example, get the
I
value
get it.
of average causal effect, and then they do a regression regression.
You mean integral regressions.
Yeah, and try to, like, for example, write a function like
Okay,
this.
so they calculate the integral area
Yes, yes.
under the curve.
So
Okay.
here we just randomly try to randomly choose some
Okay,
let me
so
see.
here the f prime is either it's just a network. Oh, I see. So it's estimate. I
Fy
see. So more like
prime.
estimation. F prime is an estimation. It's
Mm.
estimation for L1, and the L1 is actually
No. Here Fy prime is the function.
it's an
Of this.
estimation. Okay, so
Not,
okay. So but F prime you can estimate it using the
you can
Taylor.
estimate it, yeah, by the Taylor series expansion, and how they choose the mu is just the average value of your training data. So the mu I would be the average value for feature 1, and the average feature for mu 2.
It's the
Yeah.
conditional average, right? Given xi is equal to alpha, then you compute the average for xj.
No. Here the mu that's not related to alpha. So if you have your whole training data set,
So you're only
and
shooting
they
the Taylor series.
and then you just calculate the mu here.
No, but the second equation you show is a conditional expectation.
Oh yeah. And then they change, for example, if you
we fix
because
an alpha.
Yeah, fix that.
yeah, I know. Here because they let me rephrase my words. So they have proof for a given input, for example, x2, it is conditionally independent from other input like xi, x1 to
It should be
x.
independent, right? They should be independent.
So if you change the value of x2, it shouldn't affect x1 and x3 to xn.
But all of your input are dependent on the exogenous variables, right? So they are not independent.
But because you have.
So, but this is input layer, I think.
Yeah, but why do you raise the example for exogenous variables previously?
So I wanted to say, for example, if your target variable is x2, and you fix here the mu2 would be alpha, and the other one would still be the average value of your whole training data set. So
Okay.
that's my point.
Mm.
Yeah. So by doing this, and you take the expectation in both sides of the equation, so it would looks like this, and the expectation of Li, which is equals to the mu.
Yeah.
So this,
So,
so
mm.
you take both, if the you take both expectation.
And the expectation is over L1, right?
Yes.
Okay. So
Yes. So here the expectation of L1 is just equals to the mu.
it's why? Oh,
Because Li is the input, and you take the expectation, and the mu is, by definition, is the mean.
yes.
So the expectation of Li minus mu will be 0. So here we could um, erase this part, and it would become this equation. So yeah, is anyone else has a questions on this?
A little bit digesting, but I make sense of this and make sense from the very earliest.
Yeah. And by the second part, by this part, they said there's some well-studied algorithms here there to calculate this part. So so by doing this, they can calculate this faster.
Let me think about it. So we pre-calculate the means. So we pre-calculate the means. And why? Maybe I asked something stupid. I'm asking something stupid. Why the second? I mean the second option. So let me say that. Oh, sorry. We keep the Fy mu and remove the intermediate ones because we replace the expectations. But the second option still appears on the third option, a third item. And why this item? Why not this item to remove mathematically?
I think
There's
because
still
the expectation will be L1 minus mu times L1 minus mu, the transpose of, so it's not 0. So that's my understanding. Because in the mid in this term, so the expectation of L1 minus mu is just equals to 0. But here, this would be maybe Ruoban, do you know?
Is it because like you have a L1 minus mu in front and L1 minus mu after? So
yeah,
it will be a matrix. Then you cannot cancel every entry in the matrix.
You can write it. Actually, there's a matrix calculations. Right. So there's matrix calculations. Maybe I need to write it on my paper to fully digest to the equations. But anyway, so the point is that when we calculate the expectation, we are able to pre-calculate the mu, and then we just need to calculate. And what does the TR? Sorry, what does the TR means?
TR is the trace, so
The trace.
trace of the matrix.
The
So
tr-
it's the um it's the sum, right? It's the sum of how to say it? I don't know English.
Diagonal elements
Oh,
in
yeah,
the matrix.
Yeah,
I
diagonal.
think is it because for I, which is not equal to j, the two input variables are not related, so the off diagonal elements are all zero, but the diagonal elements are not zero. So we just sum up the trace and yeah.
I need to write down the equation here. So here and so when we do the calculations, then which part that we need to do on the runtime?
Which
Which part?
Can you repeat your question?
So which part? So we do not need to do it on the runtime anymore, right? Yeah, that means so we can just
So
do
the calculate of mu.
Yeah, but when we calculate
did.
mu, it can be can be pre-calculated, right? But the mu I can still be pre-calculated.
Mu I,
Mu j, sorry.
Mu j. So
Yes, mu j can still be pre-calculated.
yeah.
And so here that means for these equations, we do not need to go through the you need to go through the training set anymore. We can just calculate the mu's and calculate the partial derivatives and then get the results immediately.
Yeah.
So this is the point, right? So using the Taylor series the extensions. Yeah, maybe I'm a little bit I feel a little strange about the I know that once I'm not aware about the Taylor series, but when this goes to the equations and putting to exploitation operations, I may get a little slow. So maybe we can keep these lines and we will read that just a bit. Xianglin, please keep going on. The point here is the cashier effect can be pre-calculated with some very efficient way because of the Taylor series extension.
Yes.
Okay.
Yes. So yeah, this slides related to some mathematical functions. So but so this slides just explain what I just said. If we calculate the mean of each features, and we can just change whichever input we choose to alpha, and the other one wouldn't be affected by it because the other one is conditionally independent from each other, which is de-separated. But I don't think to prove it here is would I just don't think it's appropriate to prove the de-separated axioms here, but you can check it later. And here is how they do it on recurrent neural network. Because in recurrent neural network, we can see that the IT plus 1 and IT plus 2 is not independent, conditionally independent from each other anymore. The IT plus 1 dependent on IT, and IT plus 1 or T plus 2 dependent on IT and IT plus 1. So they cannot calculate the mean of each node anymore. So here they just adopt the intuitive thinking. So they did go through the whole training data set to calculate.
So it becomes very computationally expensive.
Yeah. But they also propose any output at time t would be only strongly dependent on input from time step t to t minus tau. So they did shrink the interval a little bit, but I didn't go through the mathematical proof here. But this is just an optimization of this problem. But here you can just view it as they go through all the training data set and calculate the value for each node. And that's how they um, solve the recurrent neural network problem. And so then we can look into the result. So the first experiment, this is quite simple. They actually construct they train a decision tree here. So we have three um, three class. One is called iris
Tosa.
Testosa, and the other one is versicolor, and the third one is Virginica.
Virginica.
And each and we have 4 input features. But in the decision tree we only use one features, the PW features, and it's quite simple. So if the PW is less than 0.29, then it would be classified into iris sentosa, and yeah. So you can look into the green line. The green line means the PW features, and from the intervention value, you can see that when the intervention value alpha is set to 0 to, like, for example, 0,
So there's still
0.3.
negative value. So the causal attribution still have negative value. All right. So because the y, so the output y has a negative value.
The output y what?
So why the ACE will be negative?
So that just means your y is less than the baseline x.
Okay, that's smaller than the baseline. So anyway, so okay, so
But
so whatever.
here
So
you can only see
so is that the area.
Mm.
So the area of the negative curve, or the curve of the negative values, the area under the negative curve matters.
They didn't mention that.
It matters, right? It actually matters because there's a difference between the baseline, the expectation of baseline. So it actually matters. So as long as it is not flattened, as the curve is not flattened, it means it somehow has some causal effect, whatever positive or negative.
But here, so they just said, look at the green line, and it did reflect the features of their model.
So it means that it has some causal effect below 0.3, and it still have the causal effect larger than 0. How to read it? How to read it somehow? So would you please explain more?
So for the class of iris sentosa, we already know that if the PW is less than 0.29, then it will be classified into this class.
Yeah.
So when you look at the interventional alpha, if the value
so
of
that means
alpha
we
is,
only need to look into the green line.
Yes. So because their decision tree only relies on the PW features.
So here I have a question that is this decision tree trained on a single variable, because there's 4 variables, or 4, the input has 4 dimensions here. Does this tree train on a single dimension or train on all dimensions?
So. Yeah, I think so.
It train on a single dimension. So in this case, for each features, it will train an independent decision tree for it.
I think so.
You can see. So for all the and also for the value alpha. Okay, so the alpha is actually in the range. So every variable is within the range of 0 and 1. So it's showing that when the alpha when the alpha giving certain values, and it cause effect or its average cause effect on
Would
these
be large.
on this alpha. So when this
Mm.
alpha is smaller than 0.2, is smaller than 0.2 comparing to the baseline, so they will causing a cause effect.
Mm.
And this baseline, let me think about it, because this baseline is, and how do they choose the baseline in this application? Have they mentioned it?
So the baseline,
Yeah.
I think the baseline would be
Suppose they choose a
the
baseline. Consider this. Suppose here the alpha. Suppose the alpha is 0.2, right?
mm.
When the alpha is 0.2 for the green lines, it will go to the iris and pulsars. But if the baseline
they
is
didn't mention the
chosen,
baseline, so I think they just use the method I mentioned before. So if they sampled the xi from the uniform distribution, then the xi here would be 0.5.
okay. So what if when suppose the so what if the okay, so there must be
So
there must be an alpha whose ACE is 0. Suppose the alpha is equal to baseline. CAC
yeah,
must be 0.
yeah,
Okay. And once this alpha is very close to the baseline, its cause effect will be 0.
yes.
And what if the PW is equal to 0.5? What if PW is equal to 0.5 and it will have a decision there? And in this case, will that be a problem?
If if
If the baseline is equal to 0.5, right? And for the decision tree, the PW is close to 0.5. And definitely we know that from the ground truth, we know when alpha is equal to 0.5.
so then
Mm,
the AC will be 0.
yeah, but actually it's not.
So it just means your your expectation of y is close to the value of baseline.
No, when P
What?
is smaller, let me think about it. So
Because the ACE is your expectation of your output minus the expectation of baseline output of baseline.
so here I think the ACE value is highly related to the baseline. And what if the alpha is actually has some cause effect when alpha is equal to certain, when x is equal to certain alpha, it actually close to certain, well maybe never mind, let's keep going on. Keep going on.
So, and then they also construct a new data set. So this is adopted from the NLP research area. So they generate a lot of sentence and the classification outcome just based on the um, first three, and this is how they train their recurrent neural network. So that's our ground truth, and the first result is their result, and the second is from the integrate gradient. But here they found out their average causal effect gives 0 for the third feature. And then they further investigate their model. So they kind of change the, so here x0 means the first feature and x2 means the third feature. So they sampled the value of those input feature and find out that when they change the value of the first feature, the prediction changes for 1,955 times. So that means the first feature would would if would affect their prediction, and they do so for the second feature and found out there's 9 times of prediction changes. So the model would be affected by the second feature. However, for the third feature, when they randomly sample the feature of X, the prediction outcome didn't change 1 time. So that means even though they try to construct the model to only consider the first 3 features, but in fact the model only look at to the first 2 features. So that prove their average causal effect is working, and the integrated gradients somehow gives you a wrong mm, a wrong
A close
interpret.
alarm, more like a close alarm. Yeah.
Mhm.
I mean, the integrated have the third dimensions from. So here, what is the blue and red means?
Mm, no, they didn't mention it, but
And the
the value
0.48
the
is actually AC
the
score.
ACE 对 yes, and
AC score.
the
But
second
but
the
there's supposed
value
to be an integrated value, right? So the AC will it consider
ACE
the
is the average causal effect, right?
yes.
So the
So
effect
it
value.
will choosing multiple alpha. It will choosing multiple alpha and integrate and sum up together. Will they do this?
Um.
Remember, AC is actually the AC, for example, for the giving alpha, we will have ACE, right? But for
Yes.
one dimension, they have a lot of alpha, or there are infinite number of alphas. So we always need to still sum up them together because here, for one vector, for input sequence,
Yeah, I get
and
what you mean. So you mean what's the alpha here, right?
yeah, so is that to sum up all the alphas together to get the score of 0.72?
Um, I couldn't give you the answer, but
Okay, so but
the
anyway,
idea is that they found out only the um first two features have positive average causal effects.
okay, those that's it.
Yeah,
So they're say in terms of RN, they compare with the
mm,
uh D
integrated gradient.
IG compare with IG. But the
Yeah,
point is why they do not compare IG with the first experiment.
uh, with what?
By right. So the previous slides, and yeah, for this experiment, for this IRES data set, it's still possible that we're using integrate gradients to do this, right?
Mm.
Integrate
But
gradients
but they didn't
always,
compare
yeah,
with.
by right. So here I think if you have times, it's worthwhile to do the assignment to compare the ACE and the IGs on this experiment. And somehow understanding the details of IGs and the ACUs actually it will be very good. So yeah, I'm not thinking about it. Maybe we can talk about on Thursday meetings or our next meetings, so we can arrange additional ones. So we can just
You mean
briefly.
to run the experiment to compare it with IG?
It's good you have tried yourself to have a deep understanding. But if you don't have time, you can just compare from a theoretical point of view of the ACE and IGs. Both are very important part. And in the future, maybe the ACE and the IGs will be used as relation for our visualizations. For example, whether our highlighted points or highlighted regions have a very high AC or IG, something like that. But anyway, so their perspective, their work focus more on the dimension wise, right? So look into which dimensions affect the model more, and also it somehow depends on the training set. That's the part that we need to think more. Okay, please go on.
Yeah, and the third experiment is did on an aircraft data set. So this is also a recurrent neural network model. So basically the model tries to predict the trajectory of an aircraft. So here we have flight parameters, which means input features, and the x-axis means the time steps. So here, the A and B is the result of um, their method, their average causal effect, and the C and D is from integrated gradient, and here B is the result of a normal trajectory,
And
and
sorry,
A
what is 0 and 15 means?
0 and 15.
So from
Where's
0, 5, 10, 15 is time lapse. So what does this time lapse mean?
where
Time
uh
lag, time lag.
time lag time lag oh means 20 seconds.
So what is the application given a features? So usually given a model, given the feature, given the input, or given output. So what does this time lag mean? Time lag, is there time lag in output?
Oh,
Yes,
it
time
just
lag.
means,
So what does time lag mean in the
I
model?
think it just means mm,
So what is the input and output of this model?
so here it didn't there's no output, but so here, for example, 0 means at time 0, and the features is listed um here.
Hmm.
So um each each um each dot is the calculate
The
average
causal,
causal
actually the
effect.
causal.
Yeah. So time lag just means um
When splitting to the time duration, and where is the
yeah,
output? And what is
there's
definition?
no output here.
There's definitely
Huh?
an output. So here, and why there are two dimensions. There's two A and what does A and B means?
So B is a
Anomaly flight.
normal,
No.
yeah, and A is a um anomalous flight trajectory. So here they just for so at any time they would have a um input features, and for each feature they calculate the average causal effect.
So go back to the previous slide. That somehow makes sense of it. So it's going to answer which parameters is part of the lateral accelerations. So here for the next slide. So here, for example, for B actually, so when the time passing by, so the features, maybe let's call it the causal features. The causal feature for the normal flat is very different for the lateral accelerations. Will be very different from those and or those causal parameters for accelerations in the normal time. So giving time, so it means that it can also using these kind of causal effects to detect the
Anomalous flight.
for anomaly detection. Right. So
Yeah.
somehow
So
this is the point.
actually they just did it to as a comparison. So they wanted to show their average causal effect can detect the anomalous flight, because in the case of integrated gradient method, there's no much difference between the normal one and the anomalous one, but in their average causal effect, you can see there's a huge difference.
But there are anomaly detections. This reference
So actually
is referencing against the train set, right? The train set.
what the you
So
mean the
so they always fix an alpha. They always fix an alpha.
here the alpha I think is just the value at that time step.
Hmm.
So
So
for
they do.
example, at the time step 0, and if we wanted to calculate the uh, um, average causal effect for the first feature, the ALT, then for this input, it must have a value for this feature, and maybe we can set that value to we can fix that value and go through the whole training data set and then get the value of this point.
Okay.
Yeah.
Okay, keep going on.
Yeah, and the last one would be the result of means data set. They they pre-trained a let me see what model. Oh, they use beta variance autoencoder to train the means data, and they defined 10 discrete variables for each digit class. So here CK means um, the class its predict class should be K. So here the A means the first picture is predict to 0. So it's related to C0 and the second picture is related to C1. And they also defined 10 continuous variables to decide the rotation and scaling. But we didn't know GK represent for what um, in advance. So here they show the result. So in
Sorry,
A we can
I missed that point. Okay, so you mean what do you can you repeat what V mean?
Z Z is somehow related to the rotation and scaling of your digit, but they didn't know in advance on um, uh, with the what ZK means. Really, they just know that ZK is related to rotation and scaling.
Okay, please going on.
So on BCD you can see that the B is related to Z0 and C8. So they are all classified into the 8 class, and C is um, related to Z6 and C8, and D is related to Z2 and C8. And you can see that B and C looks quite interpretable, but however for D, it's not. So they said maybe Z2, oh, maybe Z0 and Z6 is related to the rotation and scaling for digit 8. That's their explanation.
I'm going to ask you questions. Like how do we observe these zeros on B on the row of B? I
B,
yeah,
Z0,
the B. How do we see these zero
because
here?
because they said because B and C gives us some um, interpretable attributions on class A.
So I can
And
understand
D,
that somehow the
but
digital 8 can have the performance here, but somehow you can see the blue here means that we should not have this kind of area, right? For and red means we should have some these kind of areas. And so for A, I can fully understand for the 0, the cycle must be there, and for the blue part, the content inside the cycle should be empty. right? So that's what
So
explains
I think
Franco
here
A.
C and Z are from the latent space of the autoencoder. So
Autoencoder the
be- yeah, so
Mm.
the model
okay.
is beta how to beta VAE to train this means data set. And I think they set the latent space to 20 and said there are C0 to C9 related to the class, and there are also C0 to C9 from the latent space.
But the point is that it has already
Mm.
drawn something on the picture, right? So latent state, oh, I understand the latent space is better representations, but here is
Let
for
me
visualization.
annotate.
So
For
here,
example,
so here is
they-
not, so here is not a classification problem. It's not a classification.
yeah, so the latent space will be 20, and then they map it to back to the high dimensional space. So here we have C0 to C9. We have C0 to C9. So we have 20 um, 20 latent variable, and C0 to C9
20
related.
latent view, oh, so 20 dimension.
20. Oh, sorry, 20 dimension. Yeah, and we don't know Z0 to Z9 represent for what. So in the in B, they I think they by set the output.
Let's go back to A. I think I understand A, but now I still have some confusions on A now. So for A, it means the CK class
So
specific
outcome
latent
would be CK, and they calculate the causal effect, right?
causal effects on the pixel wise
Yes.
in pixel.
Yeah.
So for pixels, and what is the input of the, what is causal variable? So let's say given the input variables, you have an output. And the causal variables means that the causal variables, the causal dimension, right? So for each causal dimension, given the image pixels, so here, if we would like to visualize it, the causal dimension is that one causal dimension is one pixel. Suppose one pixel is very important for explanation, or it's very has a causal relation with the final output, for example, for zeros. So this causal variable must be one pixel. If one pixel is a causal variable, and it will be highlighted with either red or blue, right? So in this case, from my understanding, here we highlight every digital numbers. It's not from the latent space, it's just from the pixel wise. If I understand it correct.
Yeah.
In this case, and how this intermediate represent, what role does this intermediate representation or the Z means? What role does this mean? What role does this Z variable mean?
So I think here they have 20 variables, right? And by setting here, our input would be 1 pixels in the image. Then the output, we can set it. So here, for example, we can set it to C0. And then we can calculate the average causal effect using their method. Yeah.
So C is the label. And what is tied network? What is the tied network?
Tight network.
Target network.
Target network.
So here, for example, programs giving a target network, it has input and it has output, right? So the program definition is that we look into one dimension or several dimensions for this target network, and we're going to see whether these variables will have the causal effect for some output, right? And for in your scenarios and in this experiment, what is the target network? And I understand there's the beta autoencoders, but for these beta encoders, whether we care about the encoder part or the decoder part or both parts, anyway, and because the problem setting is for classification. We for all the experiment before, whatever the IRES network, IRES data set, the flight, the data set, or the and all the are the recurrent network, they all about the classifications. But for this experiment, there's no classifications. And what is input and what is output for this network? That's all I confused. All I get confused here.
Uh, I think uh, mm, just let me re explain this network.
So yeah, here a classification problem here or something else.
So the beta VAE just tries to reduce the dimension of means data set to 20, and then the decoder would map it back to high dimensional, right? So here we have 20 latent variable, and we label them from C0 to C9 and C0 to C9, and C0 to C9 is related to the label. So if it's C0, then somehow the digit is 0. It is in class 0.
I understand. So giving a set of the
So
zero,
here
giving
we
a set
can
of
so
giving a
here
set of zero digit giving a set of 0 digit rows, and we record all their intermediate representation or all their D, right? All their D together.
so it will look like
So
this.
here,
Remember, we can
so
write
how many dimensions does C have?
how many does C?
C is C a scalar or a vector?
C is a neuron. So C0 is a neuron, output neuron. C1 is an output neuron. So here we have 20.
So we have Z0 to Z19. If
Yeah.
C is a neuron.
No. So we split the 20 variables into C0 to C9 and C0 to Z9.
So altogether they have 20. So the first 10,
yes.
the first 10 is C0 to C9, and
Yes.
the second 10 is Z0 to Z9.
Yes.
Okay.
And the input can be the pixels. So means data set, maybe there's 64, right? See?
No, doesn't matter how many.
Yeah, so each pixel represents one input neuron. And so here for each input neuron, and for class 0, we can choose it as now output neuron, and this is our input. Oh, sorry. And using the method they propose, they can calculate the ACE for each pixel, and then you can see it in a row. Does that make sense to you? Yeah. And in the B, they set the class to they set, for example, they set CA to 1, and
Z0 to 1.
this is output neuron, and the input will be also the each pixels in the images. And yeah, so because the D is related to Z2 and C8, they think Z2 is not related to the rotation and scaling for class A, but
and what is rotating and the scaling come out? Give me explanations and how these scaling.
They just said they are related because B and C seems quite interpretable for human. So that's how they explain the beta VAE
So
network.
that somehow means that V0 and V6 is relevant.
It's
to-
responsible for the rotation and scaling for the digit 8.
responsible for the rotation.
Because
So-
they
so-
already
so-
know Z0 to Z9 is for rotation and scaling.
So the point is that so they have trained neural network models.
Mm,
So giving an arbitrary input, it could be either can be one of the 0 to 9 digits, and it to do the rotating and scalings and
Yes,
so it
yes.
will get an intermediate representations with with 20 dimensions.
mm,
So they calculate the causal effects for every pixels for these rescaled or retransformed images and draw some pixels, draw highlights and pixels. So if it is rescaled, if it is 8, even if it for the digital 8, even if rescaled, it is still somehow draw 8 on the picture. Draw so highlights the colors on the picture.
Okay, can you repeat your
So
last
here,
sentence?
so here is the so as your explanation, Z0 and C8 are 2 dimensions on intermediate representation. Intermediate representation, am I correct? And why the C8 can correspond to the images?
CA is what? Can
Why? So I really get confused. I'm not sure. I really get confused. How and for the row B and the row C. So for CK somehow means that it represents different classes, right? It represents different classes, and how these autoencoders and for the last 10 dimensions is so lucky to corresponding to each class. So I highly doubt it. And the second is that given C8 and given the 0 Z0 C8 and Z6 C8, and I think it's only about the images of 8, and it's going to track. So it somehow means that the Z0 and the Z6 is related to or relevant to or represent the images of C8.
And
So here is that means of given a CI, they are going to see whether this CI is relevant to the images of CI.
yes.
So, but it's 20 images. So why is there the Z0 to Z9? They're supposed to Z0 to Z19, right?
But we have 20 variables, and there are 10 variables responsible for the classification of.
Doesn't matter. You can see Z0 and the Z6 all corresponding to C8 because it has 20 dimensions.
No. For in the B, C, and D rows, the CA is equals to 1, and
CA. Again,
so they are
CA is equal to Z.
So they are all from class 8.
They choose the picture of 8, right?
Yeah.
They choose picture of 8, but actually the 8 C8. I highly doubt the C8 is 1 dimension in the 20. In one of is one out of the 20 intermediate representation. I highly doubt it. CA I think is just a class.
Yeah, I think it's a class.
It's definitely not the intermediate representation dimension. And for D0, so it's just going to check whether certain V can correspond to
But
certain.
they said the latent variables were modeled as 10 discrete variables for each class, C0 to C9.
So it's not 20.
10 continuous variable from Z0 to Z9. So there are 20.
Again? So why, and also why these encoders, giving these encoder 20 dimension, right? And why some of them is discrete and why some of them is continuous?
That might be related to the beta VAE. I don't know about.
Yeah, maybe that's about the structure. Maybe it's the structure, but
Yeah.
I really, maybe there's a knowledge of the,
Beta VAE.
yeah, but I think for these explanations, I feel it's very hard to digest.
But
And
that's their original word. So they said the latent variable were modeled as 10 discrete variables and 10 continuous variables.
and one and 10 of and those discrete variables that can represent the class.
Yes, they said that 10 discrete variable for each digit class from C0 to C9.
So you should explain it. So that's about the properties. So this part is very important preliminaries, and that's
Oh.
primitive for us to understand.
Mm-hmm.
Otherwise,
Yeah, so
I'm not sure how you understand or digest this part or this problem explanation. Do you think for this part is the problem to and how much you understand is that about how much you understand or how much you can explain it? So anyway, if we explain something, we need to first to tell us something about primitive. Maybe the author of the paper thinks the beta VAE, the beta autoencoders is actually a common sense, but actually here
okay.
it is not the case.
So yeah, maybe okay, then that's my bad. But they do say the 20 latent variables can be divided into two categories, and one is 10 discrete variables responsible for each digit class, and there are also 10 continuous variables for variations in digits such as rotations and scaling from Z0 to Z9. So I think that related to the beta BAE itself. So so yeah. So in the
So from
A
my understanding, so some of Z are related to C, and some of Z are not related to C. And this kind of information can be somehow visualized. But I
yes.
still get
So
confused
that
about how the
so
scaling
from
rotations factors. So basically, they have an idea that some of Z are related to C8.
yes, so that's
So for
their
example, 0 and 6 are related to C. So in this case, so they use causal information to verify what kind of Z are actually relevant and to ensure their causal
yes,
effect is effective.
that's the idea. Yeah. So they kind of use their average causal effect to interpret the beta BAE and to see what Z0 to Z9 is.
Okay, please go on. I think we do not linger on this too much.
Yeah, that's all. So that's all for their
Hmm,
work.
hmm.
Mm. So
So do they criticize why the integral gradients have some implicit bias? And I remember there's five properties, and the integral in gradients conform to the first four, but not the last one. And does he also claim there that these evaluations conform to the all properties?
mm,
And go to we can go to the last slides. My question is towards last slides. Hmm.
no, I think.
So here I have a few to-dos for you. So maybe you can present on the Thursday meetings or next weekends.
Yeah,
That is fine.
I
So
need to
first,
mention
yes.
so
Hmm.
from this experiment they show the result is they show that the latent variable z0 and z9 seems to control the rotation and scaling of the digit 8. So that's their um, conclusion from the experiment. So I think my understanding is correct.
Control the scaling and rotation of 8.
Yeah, class digit 8.
So who is doing the scaling and rotation? Humans or
Z0 to Z9. I think they are features.
so how much you understand the beta of encoder or encoder?
So, from my understanding, to use beta VAE, the encoder just map the digit to the 20 variable latent space, and C0 to C9 controls the digit class, and from Z0 to Z9, it might related to just to rotate. For example, if we have class 0 and it looks like this is controlled by C0, and maybe some zk can control 0 look like
So
this.
the beta encoder autoencoders can automatically perform the controlling and rotation performance.
Yes.
But you never mentioned that. So yeah, so I suggest that for these experiments, if you want the audience to understand.
So maybe I didn't give you the preliminary information on beta VAE.
But are you sure about these beta autoencoders?
That's their word.
But anyway, when explaining something, you
Mm.
suppose that first you need to have enough knowledge for these parts.
Yeah. So yeah,
And I'm not sure how much you understand the beta VAE, but I think you try to explain at your best. But I find that I still have some concern about whether you have enough information for the beta VAEs. And second is about we know the goal of this experiment to evaluate the effectiveness of ACE. But this experiment design is a little bit tricky, and somehow might need the structure information of how the BAE means, right? So in this case, I suggest for next slides, I suggest that as part of copying or taking the off-the-shelf slides, I suggest that you also adding some slides yourselves. And also, when you do the presentation, I suggest you go through it. Maybe you can explain to each one to see and how she could understand it. So in this case, I feel that for last experiment, I think there's a lot of confusions. Anyway, so I will check the paper myself. But anyway, we'll please go back to the last slides. And for the last slides, I think there's a few questions for ask because this is good papers, and it leaves us enough questions for us to digest and improve upon our knowledge. So will you please take notes for my questions? So we do not have answer for now, but we're definitely trying to explore those questions. So I think the capability of ask questions is very important for all of us, especially for the one who doing PhDs. So the first step, what are these 5 properties exactly this? So we should understand these properties. For example, what is symmetry? What is the symmetry, and what is the completeness, conservativeness, and of course sensitivity is fine, but and what is so-called the invariance, and all those properties, and why the IG can conform the first 4 property, but it cannot conform to the last one, and why this ACE can do the job, right? So the first question is that fully understand the 5 properties, and we may go through these properties in our next meeting. And the second is that you should grasp the idea of integrated gradients, and that is a very important concept in terms of causal effects. So we do need to understand what is integrated gradient and how these integrated gradients. So we can compare 3 approaches. The first is the straightforward or naive gradient-based approach. The second, we use integrated gradients. And finally, we look into the ACE again. And I think you have flavor graph ACE, and I think you are explained where and you can raise examples. I think you somehow master what is ACE is. But as for integral gradients and gradients, you know that, and what is integral gradient, you have a check. And then you have a table. For each column, it is one approach: gradient, integral gradient, and ACE. And for each row, there's different properties, and you're going to check whether gradient and which kind of and which property does what approach have, and you can list such a table. And if possible, you can prepare a few examples here. Yeah, so that's the two approach. That's two questions we have. And as for the last question, and that is second questions, we might need to compare on IG and ACE in detail from a theoretical point of view. I think there are no need to perform the experiment, but if you fully understand the details, I think writing code would be fairly easy. But it's good that when we comparing different approach in terms of properties, and we need a few examples. I think that's a part we need to put into discuss on the next meeting. And also that will be very informative knowledges for all of us to know. So after you get the slides, after we finish discussions on maybe next Thursdays, we can share the slides in the whole group and all the students can have a check. Okay.
Okay.
Okay, thanks, Xianglin. Overall, you have a good presentation, except for the last experiments, it caused a lot of confusion, at least to me. I'm not sure, maybe the other students can understand it well, but I'm not sure they have out of mind for the other stuff. Okay, okay, thanks, Xianglin. I don't know why I cannot mark on Zoom today, but anyway, I think, anyway, a very good job. Thanks.
Okay, thanks.
Bye.
Bye bye.